it is connected to the electrical load. Third one, field winding and armature winding are connected in series, as you can see here. Then in the compound, it will have both shunt winding and series winding. So this is the long shunt connection and this is the short shunt connection. So I had reviewed these 5 different types of connections. You can see here 1, this is 2, this is 3, 4 and 5. So 5 different types of connections of a DC machine. So this applies both for DC generator and for DC motor also. So if anybody asks you this, you should be able to clearly tell what are the different types of connections of DC machines. And here you can see we had solved a lot of example problems. I think close to 10 example problems I had explained in the last 2 lectures. So in this example problem, basically, typically the question will be to find the EMF generated. So you see the voltage is 250 volts, but the EMF generated is 266 volts as it is shown here. So slightly higher voltage we generate, and that extra voltage that we generated, there is a voltage drop in the armature. And after accounting for that armature voltage drop, remaining voltage will come as the output. So there are several, it's basically a simple application of your Kirchhoff's voltage law. Simply solving a DC circuit, you are able to get the solution. So that way. Similarly, for different types. So this is an example of a long shunt compound generator. As you can see from the circuit diagram, the shunt winding is long, and then there is a series winding is connected in series with the armature of the machine. So in this, again calculate EMF generated. So EMF generated will be slightly more than the terminal voltage. So terminal voltage is 400 volts. So EMF generated, you can expect, will be slightly more than 400. So here finally it is calculated as 404.52 volts. So this way. So these are the 2 examples, and let me go to a different page. So this is continuation of the what we have seen previously. So we had solved one more example. This is example 3, and then we have again a short shunt compound generator. Here also the question is same. Calculate the EMF induced. So again 240 volts is the terminal voltage, whereas the EMF induced is 246.87 volts. So slightly lecture 4, and the same thing also I shared on YouTube, so you should be having the video of this. Some of you might have already seen these lectures. Again, we solved one more problem here. Long shunt compound generator is considered with a diverter resistance. So this diverting resistance is connected in series with the series field. So again, it is a combination of knowing the connections of DC machine and applying your DC circuit solutions, like solving using Kirchhoff's current law and voltage law. So simply using your knowledge of circuits, you can actually solve the DC machine. So here also question asked is about power consumed in each component. So again, for different components, what is the power consumed? So I can make a calculation like this, and I can verify with the total power generated. So this was one more problem we solved. So like this, in the previous classes, I had worked out several examples. Right now I'm just only reviewing it. So directly if I jump to the lecture 5, so this is lecture 5. What you can see although on the title it is saying lecture 4, but actually it is the 5th lecture for you. So in this, what I had done, again, we had seen this EMF equation. That is, EMF generated is proportional to the poles, proportional to the speed, proportional to the flux, and proportional to the inversely proportional number of parallel paths and number of conductors, directly proportional. And then 60 is only for converting the revolutions per minute into revolutions per second. So this is a EMF induced formula and then different types. So based on these two, I have again worked out several examples also, example problems. So here you see, again there is a shunt generator, and then the question asked is about armature current, induced EMF and flux. EMF induced formula. So one more problem also we had solved. Since this is not present lecture, this is a previous lecture, I am just quickly showing you what we have done in the previous two lectures, just as a review. So again, this is one more example. So there are two types of winding, lap winding and wave winding. So in lap winding, the number of parallel paths equal to number of poles, and in wave winding there are two parallel paths. So, and based on that also there are some example problems that also we had solved, and this is the 10th, and finally I think 11th problem is this one. So basically in last two lectures I have solved 11 problems, and each problem is different, and it is something related to EMF equation of a DC machine, DC generator, and its connections. So with this, I'll just briefly give a pause, and I'll wait maybe a couple of minutes. If you have any doubts on the previous two lectures, feel free to ask your doubts. So I'll just pause for maybe a couple of minutes, and then we'll go to today's topic, which is OCC characteristics and losses in a DC generator. Into today's lecture. So today I'm going to talk about what is known as the OCC characteristics of a DC generator. So what is the OCC characteristics is open circuit characteristic. So in open circuit characteristics, what exactly you do is something like this. So let me draw it and show you. So you take a shunt generator. So this is the shunt field winding, and this is armature resistance, and this is the armature itself. And then, so the electrical load is not connected. So first I'll keep the switch open, and then there is some electrical load. Electrical load is represented by a resistance RL, and this is RA, armature resistance, and this is EG, EMF that is generated, and then this is the shunt field. So RSH is the shunt resistance. So this is the direction, so plus minus. Now to measure the voltage, what I'll do, I connect a voltmeter. So the voltmeter is connected across the terminals of the armature to find out what is the voltage. So, and on the mechanical side, so there is a shaft coming out of the machine, and then there is a prime mover. So this is the prime mover, and this prime mover is giving the mechanical input. So this is P mechanical input. So I am right in here, and then it is rotating the rotor or the armature at a n revolutions per minute, n RPM. So n may be 100, 200 or 500, whatever, it is physically rotating it. Now the question is, what is the value of the V? What is the open circuit characteristics V? So this is what we'd like to know now. So what happens is that, so the OCC characteristic will be something like this. So this is something like speed of the machine versus output voltage of the machine. So, I'm sorry, the initial part should not be like this. So the initial itself, some voltage is there. Just a minute. So what happens is that the initially the voltage is less and there is no load. So the moment you start rotating is there is some residual magnetism flux. Because of that, some voltage is generated. That will result in some current, and that current will circulate in the field winding. And the moment that initial small voltage generate initial small current, that will go into the field winding and strengthen the magnetic field. And when the magnetic field is strengthened, more EMF it will generate, and that more EMF will further generate more current, and gradually you see there is a increase in the voltage. So once it picks up a certain voltage, that is the rated voltage, then I can close the switch and then I can supply voltage to the uh, electrical load. So that way we are getting this kind of characteristic. So any, so actually one thing here, this is not speed, this is the field current, IF. So this current is called IF, field current. So all the time it is rotating at 10 RPM, but the voltage is increasing. So that is the OCC characteristic. And let me also mark some points here. So this voltage is called E naught, that is the no load voltage. So let me once again draw this more clearly. So this is the OCC characteristic, and here let's say speed is N1. Now what happens if I increase the speed? So if you increase the speed, the OCC characteristic will generate higher voltage for the same speed, for the same field current. So this is increasing in speed N2. So that means if I consider a straight line like this, so here field current is let's say IF1. For the same field current, I can now generate higher voltage uh, because the speed is higher. So that way you will be able to get it. So this is about the OCC characteristics. So if you have any doubts, you can ask now. Otherwise, I'll move forward with then one more topic on this. See, what are the conditions? See, See, what is the slope of this OCC characteristics? So if you look at slope of OCC characteristics, open circuit characteristics. So if in the initial part, if I take the slope of this, I'm drawing a small triangle here. So let's call this A, B and C. So what does AB represent? AB is nothing but voltage. And then what does BC represent? BC represents the current. So what is the slope of this line? Slope of this line is nothing but the vertical component divided by horizontal component will give you the slope. So slope will be having a unit of resistance. So for a given DC generator, given the field and field current and the voltage generated, the slope of the OCC will give you a resistance. I think it is called critical resistance. So what is the significance of this critical resistance is, let's say here initially the switch is open, but what if I close the switch and connect a resistance which is less than the critical resistance? Then what happens? It will keep on taking the current and it will not allow the voltage to build up. So therefore your voltage will not rise. You are not able to supply the required voltage. So that is why we keep the switch open. First let the voltage build up, and once the voltage has built up, only then I can close the switch and then it will start supplying to the load. So that is one more concept or point that you can note about the OCC characteristics. So this is called critical resistance. Slope of the OCC characteristics is called critical resistance. So any questions regarding this? So all right, so let's continue. So I'll go ahead and now we'll discuss a topic which is called losses in a DC machine. So what are the losses in a DC machine? So when I write DC machine, it is applicable for both DC generator and DC motor. So both it is there. So broadly, you can classify the losses into copper losses, then iron losses, and then finally mechanical losses. So what is there in the copper losses? Of course, copper losses, whenever current flows through a resistance, there will be a I square R losses, and that losses are called copper losses. And in a DC machine, there is a field winding and there is a armature winding. So the losses that happens in the field and the armature because of the flow of current are called copper losses. So these are armature copper losses. So that is IA square RA, and field copper loss nothing but IF square RF. So if you know the field resistance and the current flowing in the field, you can calculate the copper losses like that. So what are iron losses? So iron losses are the losses that happen in the magnetic core of the machine. So that's why these losses are also called magnetic losses. So there are two types again. So one is hysteresis loss and the other is eddy current losses. Hysteresis loss and eddy current loss. So these are the two types of iron losses that are appearing. So these two depends on the magnetic path of the machine. So hysteresis loss is proportional to the frequency, and eddy current loss is proportional to the square of frequency. And these are constant losses as long as the field current is constant. So if the magnetic flux is maintained constant in a DC machine, the iron losses are constant. So you can consider them as constant. So another is friction losses at the bearing and commutator, and also air friction losses. So this is basically mechanical losses are completely because of the friction. So friction will be there when the shaft is connected to the machine. Near the contact of the shaft and the machine, there is a friction loss, and also the friction loss is there because of the air. So there is an air gap, and the air is trying to oppose the rotation of the machine. That also will cause the losses. So this is called friction. So this is windage and so basically friction and windage. These are the two types, 1 and 2. Again, if the speed is constant, mechanical losses are constant. If the flux is constant, iron losses are constant. I'm sorry. So what we can do is define something as a constant losses. Just a minute. I can define the total losses. See this part. The mechanical losses are constant, iron losses are constant. Losses in the magnetic field, if the field current is constant, is also constant. I'm sorry. So let's define constant losses as WCONST, constant. And the variable losses, let's define as WVAR. So variable losses plus constant losses is nothing but total losses, W total. So these losses we can also represent in the form of power stages also in the machine. That is, let's say you are talking about power stages in DC machine. So let's, to begin with, let's talk about DC generator. So the first stage is mechanical input. So from this mechanical input, there is some losses. So these losses are nothing but iron and friction losses. Or these are mechanical losses. Then whatever is remaining, so that is nothing but actually what it is converted. So this is mechanical to electrical conversion. So conversion. So let's say I denote the input as P in. So let's call this as PM, mechanical power developed, or actually let's call it as PD. So PD is power developed in the machine. Either it will be mechanical to electrical in the case of a generator, and electrical to mechanical in case of machine, motor. Out of that, now I can remove the copper losses. both in the shunt and magnetic field, the shunt and the armature. Then whatever is the nothing but the electrical output. So let's call it as P out. So if you see, I can take the, see what is the loss expression for efficiency. So mechanical efficiency. Mechanical efficiency is nothing but, so power developed divided by input power. Whereas efficiency of electrical, for the power developed inside. So overall efficiency. So overall efficiency of the machine will be product of these two. So if I just multiply these two, PD will get cancelled. I'll get P out by P in. So this is the overall efficiency of the machine. So I think instead of just going through this kind of theory, let's work out one or two example problems. Then you will be getting a more clear picture on this. Meanwhile, if you have any doubts, feel free to ask your doubt. Hello. So I'll call it example number 12. So I'll give the given data. Just a minute. Shunt generator. Just a minute. Let me open the data of the machine. Just meanwhile, have a look at this. Okay. So the terminal voltage is 250 volts. Next, the load current is 195 amperes. And then armature resistance and shelf field resistances. So RA and RSH. So what are these values? So the armature resistance is 0.02 ohms and shelf field resistance is 50 ohms. So these data is given, and further data is given. Iron and friction losses equal to 950 watts. Iron and friction losses. 950 watts. So what needs to be found? So this is a given data. So what we have to calculate? To calculate, first is EMF generated, and next I have to calculate the copper losses. So I'll write Cu loss. So Cu loss is copper loss, and then output of prime mover. So what is output of prime mover? Nothing but input to the DC machine. Okay, and we want to find out the efficiency of the machine. So these are the things I want to find out. So can you see? Can you work out how it is done? So first part is easy, EMF generated. So how to know EMF generated? So first begin by drawing the circuit. So I have the shunt field winding, then I have the armature resistance, and then I have the armature itself. And then this is the load. So the load is taking a current of 195 amperes. And the load voltage that is given in the question is 250 volts. So if this voltage is 250 volts, then here the 50 ohms resistance is there. So therefore the field current will be 250 volts divided by 50. So the field current will be 5 amperes. So on the right side I have 195 amperes, on the left side I have 5 amperes. So total current here will be 200 amperes. So this is the armature current. But what is the armature resistance given? The armature resistance given is 0.02. So when 200 amperes is flowing through this resistance of 0.02, so at that time, what will be the voltage drop? So the voltage drop here will be 4 volts because IARA drop. 200 multiplied by 0.02 will be 4 volts. So here 4 volts is dropping. So total EG, EMF generated, will be IARA plus terminal voltage V. So this one is nothing but 4 volts plus here it is 250. So of course the answer is 254 volts. Always notice that the EMF generated will be slightly more than the actual output voltage at the terminals. Okay, so this is one answer we got. So in the question asked EMF generator, this answer we got it. Next, what is the copper loss? So copper loss will be in two places. So one loss will be in the field winding, other loss will be in the armature winding. So therefore, copper loss PCU is ISH square RA. So IA is 200 amperes square multiplied by 0.02 plus shunt field winding current is 5 amperes. So 5 square multiplied by 50 ohms. So let me calculate this. So if I quickly do it in my calculator, so this term is 800 plus this term is 1250 and total will be 2050 watts. So this is the total copper loss. So this is how you calculate the copper loss for the machine. Okay, so copper loss is also done. Next question that we have to find is the output of the prime mover. So, which is nothing but input to the machine. So, where is the prime mover? If I draw the diagram, so the prime mover is here, PM, prime mover. So, what is the output of the prime mover? So, you see what is the energy being converted? EG, IA. So, power developed is EG, IA. So, now let me make a diagram. So, this diagram which I made before will be useful. So, we have mechanical power, we have developed power, and we have output power. So what is output power? Output power is nothing but, you can calculate, that is nothing but output voltage into output current. So this is nothing but V into I. So in our case, what is the voltage into current? So let me do that. P out is nothing but output voltage 250 volts multiplied by output current 195 amperes. So go to the diagram, you notice that the load current is 195 amperes and load voltage is 250 volts. So based on that, what is the total output of the machine? So 195 multiplied by 250, it is 48,750 watts. Now what is the difference between these two? So here I am getting 48,750 watts. So here I can show copper losses. So just now we calculated copper losses 2050. So let me put the copper losses here to be 2050 watts. So therefore it's a simple addition now to know what is the power developed. So if I add these two, then I'll get the total power developed. Okay. So that is the addition of these two. So power developed is power output plus copper loss. So that is 48,750 plus 2050. So how much is it? So I'm getting 50,800 watts. So this is here power developed 50,800. So there is another way to know what is the power developed. So the another way to know what is the power developed is nothing but your EMF generated into armature current. See, power developed is also equal to EMF generated EG into IA. So what is EMF generated? 254. Now if I multiply with 200 the armature current, this also gives you exactly the same amount, that is 50,800 watts. So this is just to confirm your answer. So this is nothing but EG into IA is equal to. So this is V into I, whereas this is EG into IA, 50,800 watts. Now what is here? So here you have iron and friction mechanical losses, iron plus friction losses, windage losses and all these things. So in the question that is given, that is 800 watts, the data it is given. So therefore now to find the prime mover input prime mover output or the mechanical power input, I just have to add these two numbers. So I'll get 51,600 watts as the total input power. So let me write it here. Power mechanical is nothing but power input. So I can just the notation. It is nothing but power developed plus friction and windage losses, F and W, and iron losses. So therefore here I am getting 50,800 plus 800 and this give me 51,600 watts. So once I know this, I can find the efficiency. So how to find the efficiency? So here, if I take the ratio of these two, I'll get the efficiency of the electrical part. So that is nothing but efficiency of the electrical part is nothing but output is 48750. Power developed is 51800. Whereas efficiency of the mechanical part will be, what is the input to the mechanical part? That is 50,880, whereas the input is 51600 and the output is only 50800. And overall efficiency of the machine is nothing but P out divided by P in of the total machine. So that is nothing but 48750 divided by 51600. So let's quickly calculate these numbers. So this one I am getting 95.96%. And this one I am getting 98.45%. So this will be actually the product of these two. So it will be slightly divided by the armature current, that is 198.93. And when I do this, 16.3 divided by 198.93. So I'm getting 0.082 ohms. So this is the armature resistance that we are able to calculate. So this was one part of the question. So any doubts so far? So now, given the armature, since the time is almost up, so what I'll ask you to do is take this as a homework. Okay, so homework. So the homework is create a plot. So on the plot, what I want to do is on the x-axis, I want the armature or the load current. And the load current starts from 0 amperes to, let's say, 200 amperes. And I can take steps of every 10, maybe, 10, 20, 30, 40 like that. Sorry, 10, yeah, every 10 amperes. So that load current, and on the y-axis, I want to find the efficiency. So of course here the efficiency will be 0 when the load current is 0 because P out is 0. So how the efficiency is varying with this thing. So assume load voltage is maintained at 230 volts always. So how are you able to maintain the load voltage is that by increasing the speed of the machine, you can generate more or less voltage. So as the load varies, I can control how much voltage I am generating. So it's kind of a voltage control kind of a mode. And with that, class, which I'll take on Thursday, I'll ask, I'll start the class by asking you what is the maximum efficiency and at what current the maximum efficiency is achieved and all these kind of questions. So try to create the plot something like this. Okay, so with that, if you have any final questions, I'll wait for that. Otherwise, let's conclude today's class and we'll meet for the next class on Thursday.